Today we're introducing imaginary numbers. In the past, you've been told that you cannot take the square root of a negative number. Since x times x is equal to x squared and negative x times negative x is equal to x squared, the square root of x squared was always said to be equal to x or negative x. Since you can't multiply two of the same number with the same sign together and get a negative result, you could never take the square root of any negative number. We've always been told to put no real solution. But now it turns out that there was actually a need for rooting negative numbers, and in particular today, taking the square root of a negative number. Electrical currents, quantum mechanics, signal processing like your cell phones use are some examples of fields that needed a way to have numbers that aren't real. Just to review, real numbers are made up of rational and irrational sets of numbers. That basically includes every number you know so far. But now we're going to introduce the imaginary number. We just call it I. Notice how it's a lower so that we can tell it apart from other lowercase i's. Square root of -1. I literally equals the square root of imaginary number I allows us to do is to simplify roots with negative radicands or the square root of -25. I'm going to skip a couple steps here, so don't. Square root of 25 times the square root of -1. Well, since we know the square root of 25 is 5, and now we know that the square root of -1 is I, two values together, and come out with 5i. We always write the real number before the I. I shouldn't call it a real number because together it makes up an imaginary number, but I always write the actual number before I. I would never switch that around and write I5. Let's try again with the square root of negative. That's going to be equal to the square root of 100 times the square root of -1. We know the square root of 100, and now we know the square root of -1. When I multiply them together, I simply get 10i. Remember that a square multiplied by itself gives you back the original radicand. In other words, roots and powers are inverses and can basically cancel each other off the page. So, when I take square root of 3 and multiply it by another root 3, I get square root of 3. Second root and second power basically inverse each other out of the way, and I'm just left with a 3. Keep that in mind as we look at the square root of -1. Same thing applies. When I square a square root, they basically cancel each other out, and I'm left is equal to -1 because I times I is the same as I squared, and that equals -1 because square root of -1 is I. So let's take a look a little further. We can say that I to the first power is equal to I, right? Anything to the first power is equal to itself. I squared, we just discussed. What about I to the third power? If I multiply 3 of those roots together, 2 of them will give me back a value of -1, and I have this third odd man out that gives me a value of I. Multiplied together, I get -I. I can do the same thing for I to the fourth. I promise there's a purpose to this. Now 2 pairs of -1s. Multiplied together, -1 times -1 just gives me a final value of +1. So I have my first 4 powers of I, -1, -I, and 1. I could have started at I to the 0 power. Anything to the 0 power is 1. So kind of keep that in mind and just, well, the importance of these 4 values will make itself clear as I show you the next 4 powers of I and the following 4 powers of I. Can you see the pattern? Every 4 powers of I repeat those same 4 values. And this is going to go on forever. It's going to make it so that we can simplify I with really large exponents by using those first 4 exponent answers, right? Those first values. Basically how it works is if I take the exponent and divide it by 4, since there's 4 different values, and find the remainder, that remainder is going to tell us which of those first 4. Let me show you how this works. Let's say we want to find I to the 123rd power. We're going to take 4, and I'm going to do a little bit of division here. I'm not going to finish it. This is actually 30 root 3. That's important. A remainder of 3 says that I to the 123rd power, and since I to the 3rd is equal to negative I, then I to the 123rd is also equal to negative I. Just a reminder that a remainder of 0 is the same as I to the 4th because that had exactly the same value as I to the 0 power. We probably should have started with I. So just a couple more definitions. When I'm adding or subtracting an imaginary number, to combine like terms, all kinds of things can take place. They could be squared when they're multiplied. Let's take a look. When I have a number where there's a constant, which is a real number, added to another imaginary number, we're going to call that a complex number. Some people say complex, some people say fine, just so that we're on the same page. But let me show you what a complex number looks like. If I take the real number 7 and the imaginary number 2i, when I add them together, it becomes a complex number. The real number negative 1 added to an imaginary number, complex number. 3 and negative 5i, real and imaginary, when they're combined or added together, becomes a complex number. It's important to identify the real part of a complex number, the imaginary part of a complex number. They're only called complex when they're added. The general form of a complex number, just so we know, is a plus bi. You always put the real portion first and the imaginary portion second. A is called wholly real because it has only a real number. Bi is the imaginary this complex number, and if only that existed, we'd call it wholly imaginary. And of course, together they're a complex number. That's going to wrap it up for today. Make sure to write down any questions you have so you can remember to ask them in class. And I will see you on the flip side.